Welcome to our FAULHABER Drive Time. In this video, I want to check the influence of different encoder systems to the control loop performance. And to do so, I got different motors. I usually would use the 22mm ones, where we do have the linear Hall or a magnetic incremental encoder or an optical incremental encoder or the Absolut encoder, again magnetic, either single turn or multi-turn. But for your benefit, I don't use the small ones, but I'm going to use the big ones here, 32mm diameter, because then it's easier to watch them in the setup here. But reconfiguration here, once again, hooking up all these motors takes some time, so we are going to use some time-lapse and cuts in this video to have you concentrating only on the main aspects here. In the end, we will see me using the drive configuration window and the tuning window, and then in the end I will summarize the results with a single slide. So let's start this. Let me grab my PC and we can start here. So here with the first one, it's the one having the linear Hall sensors here. Okay, I have to connect it to the motion controller. Only two connectors in that case, and can start configuring. And first one, of course, select the motor, and that's still the one that I used in the last videos. So here, that's the bigger one, 3268, and it's a 24-volt execution, and it's having linear Hall sensors as the one in the first videos had. And as I only have the linear ones, these are going to be used for all the loops. Once again, the check for the supply voltage with the threshold, and then transfer the configuration. And for the linear Halls, there's always the option to adjust the Hall sensor signals, so to teach in the Hall sensor signals to the controller here. And this takes a few moments and is better done without any load connected to the motor. The disk doesn't harm here, but no friction or something like this. And that's a one-time exercise that we have to do to more or less pair the motor and this controller, and then we are done here. I could save the parameters, but I don't have to. And then I'm using the configure controller tool to identify the inertia. I'm doing this once only here in this video, because of course it's always the same motor, same disk, so I can use this value for the next ones too. Use the startup method here. It's a pretty small disk, at least compared to this motor here. Okay, check the result. Yeah, a factor of roughly a little more than the idling motor here. And again, transfer the configuration, and that's an important step because now all the control loop parameters are preset for the now identified inertia, and of course for the motors that I selected here. Transfer configuration, and I'm done here. And again, I don't need to change it, save it, and then use the controller tuning, and always the same steps here. So first check the speed response here, somewhere in the middle of the operating range, and the standard behavior of such a speed loop, and some ringing on the right side here. That's due to the sensor system that is used here. I usually directly enable the feed-forwards and reduce the loop parameters a little bit to have more headroom to compensate for disturbance, and I can as well try to increase the loop gain a little bit. Yeah, a little more would be fine. And then directly switch to the position loop and do a single step with the parameters. And we now see following is perfect, so there's almost no deviation between the demand position and the actual position. Speed is up to 50% of the, that's the dotted yellow one, of the maximum speed that this motor could reach, and the current is close to the 3 times the nominal current, but there is still some headroom here. So I can now save the result here as a CSV file, and this is what I'm going to use later on to compare the results of the 4 motors. Let's use the next one. The next one is the same motor, but here now having digital Hall sensors and a magnetic incremental encoder having 1024 lines per revolution. So steps are now, once again, select the motor here. It's didn't save it in the last take, and so it's the long one, 3268, 24 volt execution. This one now has digital Hall sensors for commutation, and we do have an incremental encoder having the 10 to 24 pulses per revolution. I do have an index, and in that case, for commutation, it would either be the digital Hall sensors or a combination of Hall sensors and encoder, and I'm going to use that one because then I can use field-oriented control or sinus commutation. And for the velocity loop as well as for the position loop, I'm going to use the incremental encoder. And once again, the check of the voltage range, and then here's the summary of the parameters, and then we are done here. And the next steps are going to be time-lapsed, because these are essentially the same that we had in the first step, and so we only check the result afterwards. So. And again, close to perfect following. The maximum speed is the same as in before, and the current is similar, and checking the control loop, that's stable here. So I once again can save the parameters, and then I'm done here. Now here is the same motor, again digital Halls, but in that case it's an optical encoder, the IER3-10000. And let's do the same here. So first of all, of course, I have to once again walk through the configure controller window here. Same motor, same execution, same winding, but now it's a different resolution here, 10,000 increments per revolution. And the next steps then are identical, so I'm using digital Hall sensors plus encoder for field-oriented control, sinusoidal commutation, incremental encoders to close speed and position loop, same voltage check here, summary of the parameters, transfer the configuration, and so on. And now here it's more or less the same general behavior, but we do have less ringing on the right side here with this optical encoder, because the optical encoder is a very precise sensor here. But again, I do add the feed forwards and adjust the profile parameters. What I can do here is I can increase the gain of the speed loop significantly, because there's almost no noise in this encoder signal here. So I do have some headroom for better compensation of disturbance. And now switch to the position loop, and what I have to take care of is a different resolution here. I do have 10,000 lines per revolution, which gives me 40,000 increments per turn. So when I want to have a single turn of the motor, I have to change the set point here, do one check, and then again that's perfect, and I can even increase the gain of the position loop here significantly without getting unstable. And now that's really a very tight control here, and you don't see any oscillations on the current or on the speed here. That's the benefit of this specific encoder compared to all others. Again, save the results, and we are done for that one here. So here's the last one out of the series. It's the one having the magnetic Absolut encoder. In that case, it's a single-turn encoder having 4096 increments per revolution, so a 12-bit. We would have an optional multi-turn encoder too. In that case, I wasn't able to get such a motor on short notice with the Molex connector, but this doesn't matter. I can use our standard adapter board here, which is giving me more options in terms of connectors that I can use here for the connection between the motor and the driver. So I can hook it up, and then this is going into the encoder connector here. Okay, we are done. And now let's do the configuration. Same motor, but now we are having a different sensor system. We don't use any Hall sensors at all, but we do have an Absolut encoder, and the default is the single turn, having these 12 bits for a single turn, and no multi-turn information. As mentioned, there would be a multi-turn available too. And then, of course, this single encoder system, the Absolut one, is going to be used for all of the loops. The benefit of this Absolut encoder is that this one is, with its line driver, the one that might be best for, let's say, a little longer wiring between the driver and the motor, but take care of your shielding and grounding in such a case. And then same steps, adjust the voltage control, summary of the parameters, transfer configuration, finished. And once again, a first step for the speed loop. Yeah, and there's a little more noise compared to the optical encoder, but in general it's fine. I can use the same approach, so apply the feed forwards here and adjust the profile parameters, and I might as well increase the gain here a little bit and directly switch to the precision loop. And now, of course, for a single turn, I have to once again use a set point of 4096 increments. And let's do this. There is one step. And again, perfect following, it's fine. I could increase the gain for the precision loop to be more robust against disturbance, but I think that one is fine here. And could now save the parameters, but what I want to do in a first step is that for the Absolut encoders, there is an option to actually try to compensate the whatever errors the encoder might have. And so to use it, the motor has to be idle, so no load connected, because it's going to be operated at a significant speed, and then when these conditions are met, start the optimization. It's recording the data and calculating a compensation table out of the speed and position that is captured right now. Okay, and then I'm going to save these values here and once again switch to the controller tuning. The settings for the speed loop are still the same. Let's directly switch to the position loop and have a single step response here. Yeah, and that's very close following here, almost perfect, and save the data, and then we can prepare a short comparison between the behavior of these 4 encoders. So here is the comparison between the 4 encoder systems on a single page, first for the step response, and the next one is going to be for the position. It's always been a step to 1000 RPM, and the yellow line would be the demand speed, whereas the green one is the current and the blue one is the actual speed. And we can see a very similar behavior for all of them, but obviously for the magnetic ones, that's the left column here. On top it's the magnetic incremental, and on the bottom it's the magnetic absolute. This is a behavior which is very similar when we compare these small oscillations here. On the right side, it's the linear halls on top and the optical on the bottom here. And when we compare the oscillations in the actual speed, the blue line here and the blue line down here, we can see that for a constant speed operation, the optical encoder is superior. So it's got the lowest oscillations in this speed loop because it's got the highest precision, lowest error that we have in these encoders. When we now compare the reaction in a single turn of the motor, there is a blue signal and a yellow signal, which are the actual value of the position and the demand position. And in all of the 4 pictures here, we have a very perfect following of these 2 lines. The green one is the triangular speed here during this move, and then the remaining one would be the current here. And when we compare them, it's very similar. So for position loop, there isn't much difference between the linear Hall and even the optical one, at least while we still use the standard parameters for these motors. The optical does have its benefits because, as I explained, I can increase the gains here and would have better compensation of the disturbance. A table to compare the results. These are the 4 sensor signals that I used here, and then this is the response to a speed step. It's first the rise time, which is the time from 0 speed to first being into the corridor of the target speed, and the settling time, which is the time that we need from starting at 0 to finally be in the target corridor. And as you can see, the optical one is pretty good in that case here, whereas the other ones take some time due to the ringing that we've seen. For the time per single turn, these ones are pretty similar here. It's the same resolution and similar precision of these encoders here, whereas the optical one with the default settings would use the same time, but it can be tuned due to the higher gain for the parameters and can be pretty fast in such a case, and that's due to the better precision of this encoder. Of course, in that case, gains have been increased and the braking chopper has been used. So far about the influence of different encoder systems in a control loop. If you got any questions about the encoders or the motor controls itself, don't hesitate to contact our local sales team or contact our MC support team. And of course, feel free to leave a comment below the video here. Thanks for watching, and check back with our channel and bye.